Yeah, thanks for inviting me. Yeah, I'm here to present NOMAD, which we call a fair data sharing platform for material science. And yeah, material science, those of you that know NOMAD, you know that it has a very strong focus on electronic structure simulation data. But this is also why I wanted to talk about FAIR-MAT. And FAIR-MAT is an NFDI consortia. In fact, we are starting with tomorrow. Tomorrow is our official start date for this project. And the goal of FAIR-MAT is to bring data sharing to a wider material science community. And this is where we want to use our NOMAD software, our experience that we take from DFT simulations, electronic structure codes, and offer this to the whole community of condensed matter physics. So yeah, I want to start a little bit with like a high level overview, talking a little bit about what NOMAD actually is. For those of you that don't know it, and then I want to also do the same thing on FAIR-MAT, and then I want to go a little bit more technical and explain to you how NOMAD does work internally, what architecture we use, how it's operated, how does it work, how could you extend it or use it for yourself, all these kind of aspects. And then hopefully in the second part, I concentrate more on an idea that's the NOMAD Oasis, which is the idea that you can use NOMAD also locally in your institutes. And this is all what we want to use in FAIR-MAT mostly, to build really a federated network, a federated data sharing network where everybody can participate and we basically distribute the data over the globe and thereby making it fair and accessible to everybody. Yeah, so that's the plan for today. So yeah, let me start to hop in and talk a little bit about what NOMAD is. So we characterize NOMAD as a fair data sharing platform for material science. And here we have two parts. The first part is the data sharing. And we think that data sharing means, and this is in contrast to many other material science databases that you might know, that we are not hosting our own data, right? We are really there to share the data that others provide to us. So the goal is to make your data, the data of the regular researchers, available to others. So that's the fundamental thing of our platform. And the other part is the material science part. And this means, and this is also in contrast to other platforms, like where you are more about generic data sharing, when you think about Zenodo or when you think about Google Data Search or these kind of things. What we want to do is really to be domain specific. We want to extract rich domain specific metadata from the files or from the data that is provided to us. So it's not just about identifying the author and the title and abstract and stuff like this. It's really about digging into the data and finding out what are the specifics. What is the chemistry? What is the concrete crystal system, the structure, whatever that was measured or simulated? What are the parameters used? What are the material properties that were calculated or that were gained by any other means? And currently, NOMAD is mostly about ab initio calculations. But of course, and this is where FAIR-MAT comes in. We want to extend this. We want to also open this up to experimental data, to data from synthesis, from data on different scales of computational material science and so on. Yeah, and NOMAD, in NOMAD, all the data is visualized. It can be downloaded, it can be browsed. We have like a search interface. It can be browsed in a common format with a common schema. It has a graphic user interface. It has an API so that you can work with the data programmatically. I have a few screenshots here. The first thing that you see is like our search interface, for example, and then you see like the visualizations, the overview that we have for all the data in there. Then it really depends on what data is about, right? To really see different charts with different properties on it. We also have like this detailed view, the archive, where you can really see all the different numbers and data points that we identified in the data that was provided to us. This is what like later we will talk about a lot about the archive and how it works. And we also have like an analytics platform, like Jupyter notebooks that are run directly on our servers that you can use to access the data and to do some analysis on it. And then there's the whole data providing part, right? So it's a publishing platform. It's really about like people giving us their data or share the data through the NOMAD platform. And we allow everybody to have a simple process of uploading their data. It's completely free. Everybody can publish their data. You can have an embargo on your data, to assist the publishing process. You can get a DOI on your data for your papers for referencing. And then you can share your data with either in private with reviewers, for example, or with colleagues, or like public with everybody. Yeah, that's the whole idea about NOMAD, right? To summarize it a little bit, you could say that NOMAD is there to assist the overall research process. You basically want to do the same thing that the publishing world is doing to papers, we want to do for data, right? So we want to enable everybody to publish their data.
Your audio is currently stopped, at least in our place. I'm not sure.
Okay, let me check.
We're back. We're back.
Okay. Okay. I hope there will be no more interruptions. I have no idea if this was on my side. Yeah, we will see. Let me know if anybody else can't hear me. Just let me know. So where? So yeah, basically we want to do like the publishing game, but with data, right? So it starts with data on your hard drive, and then we allow you to upload your data, and then we allow you to publish your data, and then you publish data that everybody can see. That everybody can explore through our search interface, that everybody can have a look at and see visualizations of data. And then, of course, you can analyze the data with services that we provide. And then the cycle closes, right? So you get inspired by other people's data. You want to reproduce their findings, or you want to do similar analysis or do similar experiments or whatever. Then we are back to you and the data on your hard drive, and the circle begins again. So that's like the overall picture, like having NOMAD as a set of central services, like a web page that you can go through and that you can put your data to, that you can also use to see what others have put up there. And then there's this other idea that I briefly mentioned in the beginning. We could also allow people to use the NOMAD software, locally and have their own NOMAD, right? Why not? NOMAD is just a piece of software in the sense that we run on our central servers, but in principle, everybody could run it. And this is what we like to call the NOMAD oasis. And here the same thing applies, but you have like shorter cycles, right? You can upload data to your own NOMAD. You can share it with your colleagues in your institute. And then, of course, at some point you can say, okay, my data is ready now. I want to publish it and move it to central NOMAD. But even with your local NOMAD, you can do the same things. You can use the search interface to explore the data that's available at your institute that your PhD students were putting in or whatsoever. So the idea is like you never really lose the data of some PhD student left your institute or that left your group or something like this. And of course, you can use all the analysis tools that we have. Yeah, so that's the other big idea. Like besides having like this overall publishing, we really want to make NOMAD available for your daily work, right? Have it at your local institute, and really use it to manage your data. So it's not just about publishing it after the fact, after you're done, and basically you're just about like to write a paper and then publish it. But even in between, for all the intermediate results, it might be a good platform, a good useful platform for you to just manage your data. In this slide, I wanted to highlight a little bit that NOMAD is not alone, but it's a large ecosystem of similar projects or related projects that fulfill like different tasks or that have different focuses in this whole thing. I put NOMAD in the center. You don't really have to read everything. I try to highlight a few things where we differentiate from our colleagues. So one set of very similar things are all the big databases that you know, like something like Materials project or the Aflo library, stuff like this. They have like these high throughput workflows that constantly produce new data, and then that they show with a web application, right? So they also have like a search interface usually, and you can see the data and download the data and do something with it. The big differentiator, of course, is that NOMAD tries to be a platform where everybody can put their data. It's not just about our own data, and this comes like with unique challenges, right? When it comes to like curating the data and taking care of data quality and stuff like this. Then, of course, there's this whole realm of having methods that provide data, right? Having electronic structure codes that allow you to do simulations, having workflows that allow you to do lots of simulations at the same time, but also look at other branches of material science like instruments and electronic lab notebooks and stuff like this. Like there's the huge amount of projects that produce data, and with these projects also there's a huge amount of data formats that need to be supported. We will talk about like data formats and how to convert them and how to find metadata later in the talk. And then there's this whole other side of databases when you think about having just general databases or having something like Zenodo where you can share any data, right? These very generic platforms that allow you to basically put up data, get a DOI, put it in your paper, and then others can download it, which is fine, but it has like on the negative side, it's really hard to identify data in order to find the exact data that you want. Like if you ever try to use Google Data Search and try to find like a simulation for a specific system that you're interested in or for a specific material, it's not easy to find anything in there because like the only thing that Google indexes is like the titles of people that gave people the data sets and stuff like this. And then, of course, we have all the research networks like the Deutsche Forschungsnetzwerk or the European Open Science Cloud or these kind of things, which are more like political initiatives, but where it's all about like connecting the dots and having databases interact with each other. And this is where FAIR-MAT plays more like an important role for us. Where we want to use the NOMAD software to build like a larger network of connected repositories and also connect to other repositories out there. Yeah, so that's the, and yeah, one last thing I wanted to mention is standards, right? Data formats, of course, are tried to be standardized when you think about something like Nexus that you might have heard of. But there might also be in the future be standards for like larger schema efforts for like having joint ontologies like the MO for material science, for example. And then there are API standards. One thing that a lot of us are working on is the Optimate standard for having like a specific standard for an API that allows you to connect to material science databases in a common way so that it's easier for you to use multiple databases at the same time. And this also makes it easier for projects like FAIR-MAT, for example, to connect databases because like, it's much easier to get data in a consistent form, to retrieve data or search for data in a consistent form. Okay, that's what I wanted to say about like, the related work and the related stuff. Some of it will come up later again. Let's continue with talking a little bit, first summarizing a little bit NOMAD and then seeing how it plays into the whole FAIR-MAT idea, or what FAIR-MAT actually is all about. Yeah, so just to summarize, like NOMAD at the moment is a set of central services. There's a website you can go to, and then you can basically do all the stuff. You can take your computational material science data, zip it up, and just upload it to NOMAD, publish it. And then others can see what you have published, right? There's a search interface, and then there's means to visualize and analyze the data. And the source software package, in principle, could also be run on different servers, right? That's the whole NOMAD Oasis idea. And this is what we want to do with FAIR-MAT. Yeah. And the reason is like NOMAD is like already a long-running project, and we have like quite some experience with dealing with metadata. And even though it's like focused on a specific domain of materials, but we really want to bring this experience then also to the other domains. Right? So NOMAD was like a little bit of history. NOMAD was created like almost like 7 years ago. And by now we are accumulated like over 11 million code runs that were basically published on NOMAD. We have like over 100 terabytes of raw data. That's like all simulation input and output files. And if you calculate all the different quantities that are in there, like all the systems that go in there, all the elements that go in there, all the energies that are calculated and everything, you come up to like over 7 billion little pieces of information that are in the database. We support over 40 community codes, so almost all electronic structure codes you might find are supported by NOMAD. And all the data that we have is made up from or was provided from over 400 researchers from all over the world, including 3 of the large high throughput databases, OQM, Diaflow, and the Materials project. Around 250 users daily reach our website and use our service in some capacity. Yeah, and now in FAIR-MAT, we basically want to do the same thing, just on a larger scale. We want to use the NOMAD software. We want to still have like a central kind of installation. But now that we are looking into like different kinds of material science, it might not work this way in all cases. Like, for example, we imagine that we have institutes that run experiments that produce like a large amount of data. Data that's so large, like when it goes in the terabyte or petabyte regions, where a centralized idea isn't just working anymore, right? And we really need local repositories, or the institutes really have to take care of their own data. And this is where the idea of the Oasis comes in, right? So people, institutes could run NOMAD software in their own institutes, and then we just have a connection to the central system, right? And the central system then more acts as a central search index, so to speak, like the Google for material science. So we only transfer some of the data, we only transfer the metadata to the central system, and thereby allowing to publish the data, or at least publishing references to the data, while the data stays at the local institute. But the central installation will then make the connections that allow people to reach the different installations. And then we have to accommodate like certain different scenarios that we might expect. So other institutes might have like a different thing where they already have like existing data infrastructures, they already have existing repositories or ways of means of managing the data. But we still think that the Oasis can be an important role, and then basically be put on top of it as an interface, basically, to allow the connection to the central servers. Or we might have institutes that run like larger laboratories where lots of instruments need to be connected, where electronic lab notebooks come into play. In essence, just a different source of data. And again, we think that we can use the NOMAD software as a local repository. But there might also be institutes that say, okay, the NOMAD Oasis isn't really working for us. We need like a different set of features. But then still, through API standards and stuff like this, we are striving to make a connection and to allow to index this data on our central installation. Yeah, that's like the overall idea. We really want to build like this network of repositories. And in order to do this, there are like certain tasks and challenges that we have to address. Like the biggest one, or one of the biggest one, and I think that was also discussed here at this workshop in some detail, is like metadata. How to define the metadata, how to align the metadata, right? Different methods mean different metadata, but somehow it has to put together. So that's one big part of the FAIR-MAT project, dealing with metadata. Then, of course, all these repositories have to be established, right? The NOMAD software has to be further developed. It has to be adapted to this Oasis use case, and then we really have to build these local repositories. Another big challenge. And in FAIR-MAT, we basically have 5 bigger experimental methods on board, or institutes that represent these methods. This is basically what we want to start with, and then lead by example, and then hopefully connect to more and more institutes and to connect to more and more different methods. By the way, do you see the map of Germany in the background? That's just because, like, at the moment, NFTI is like funded by Germany, but of course, all these ideas should apply to the whole world. And yeah, another thing is like the central thing, right, which we in the context of FAIR-MAT like to call the portal, and this is where all the data becomes fair in a sense, right? This is what makes data findable, what makes data accessible. That's the central gateway that everybody goes to actually reach the data that might then be stored in different repositories. And then, of course, there's lots of efforts when it comes to connecting everything. Like, we really have to see this as a connected network, and not an isolated network, right? And then there's also efforts to connect this to like larger research networks, like the Deutsche Forschungsnetzwerk or the European Open Science Cloud. And of course others as well. And then another big point in this whole FAIR-MAT thing is like electronic notebooks and laboratory information systems, like local IT infrastructures that already connect laboratories and the different tools and instruments that are used there into each other, which is like, yeah, on a local scale, very important for us to integrate the data already and provide metadata in a sensible way, so that it's not just about like singular measurements, but really about like whole experiments and workflows and stuff like this. Yeah, this is a little bit what we plan for the FAIR-MAT project, or what the different focus areas are, and how the overall architecture that we envision should look like. And for us, the important thing is to really have this like a connected network and reach out to the community and basically make people work together and yeah, build this network together in order to have to finally have a way to really make the data reproducible, to really share the data, and not just having papers where we write about your data, but really make your data available and make others help others use the data. Okay, that was my high-level overview about everything. I took quite some time on this, but I think it's important that you get the picture. I will increase now a little bit in speed to get some of the technical ideas out. Yeah, how does NOMAD work from a user's perspective, right? Yeah, it starts all with the files that you have on your computers. Like imagine that you have done a few vast DFT calculations, for example, and you want to publish them. Typically, what our users can do is they just take all the files that they have as they are, they just put them into a zip archive or into a tar file, and then they just upload it to NOMAD. And then on our sides, we basically extract the archive. We go through everything that you provided, all the files that are there. And we just try to look for files that we recognize. And this is what we call the main files, right? To each file that we recognize, for example, the vast1 XML, or something like this, will then represent a new entry in NOMAD. And then that entry might consist of more files, but it's the one is the main file, and then you have like auxiliary files or your input files or other files that you generated or files that you just put into the same directory. This is what we call auxiliary files. And then we put our parsers on the main file. Like for each of the different codes that we support, we have basically a parser, and then the parser digs into the file and tries to find all the information and to very fine detail. And then it transforms this information, this data and metadata, into a common format that we call the archive. So each entry will get one archive, and this archive provides all the information about the applied method, the studied system, the calculated properties, and more, and everything under a common scheme and the common format. Entries for similar systems are then aggregated into materials, and this is what we call the NOMAD encyclopedia, where we basically collect entries that are simulations that were done for the same material, and yeah, provide them in a way that you can see, okay, for this material, these and these kind of information were put together. And all the data, all the raw files that were provided, the archives, the entries, and the material data is all available through our user interface, but there's also like an API that you can use to work with this data programmatically. And we also provide a Python library that you can use to like easily use this API to get the data and extract certain archive parts that you like for analysis, for example, in your local Python environment. Or you use our analytics toolkit where you can run the Python directly on our servers. Yeah, let's talk a little bit about the archives. So, because these are really important for us, the NOMAD archives, our common file format is the basis for everything. It provides the necessary metadata for our search system, for our representation and visualization in graphic user interface, for the encyclopedia, and also for analysis. This is what the typical archive looks like in our user interface. The archive is basically a structured format. It's hierarchical. Everything is structured into sections. Sections can have subsections. It's like a book, basically. And then sections can also contain quantities, right? Like the actual data. So in this example, for example, we see like a typical archive for a simulation run. So we have something like the section run, and then the section run is subdivided into a section method where everything about the method goes, a section calculation where the calculation results are going, and a section system that describes the system that was simulated. And then in this example, we dove into the system, and you see all the quantities that make up the system, like all the site positions and the atoms there, and what the lattice is, and all these kind of things. So you see some visualization of the system here, and then I highlighted the lattice vectors, and you see like a mathematical representation of what the lattice vectors typically look like a 3x3 matrix and stuff like this. So this is like our archive. Like we really try to dissect all the information and provide it in this hierarchical form. Yeah, let me skip this a little bit. I think you're all pretty much familiar with this, what data and data schemas and metadata are. Let's talk a little bit more about like how to homogenize like heterogeneous data or metadata. I use like different colors and different symbols here to represent different things. So when you look at a structured metadata file, for example, there are two things to consider. One is like the information inside that might be heterogeneous. One method like really produces completely different information from another method. Like a microscopy picture is a completely different thing from a DFT calculation. And then another thing, this is what I want to represent with the symbols. And then another thing is the colors, which is like the data format, right? JSON is different from HD5, and then ASCII is different from XML, and these kind of things, right? And these can be considered like separately. Converting the data format is usually the easier task, right? Because you basically keep the same information structure, you just change the underlying bit-by-bit representation of the data. So getting rid of the colors usually is not that big of a problem, right? It usually needs a converter or parser of some sort to read the information and just write it into a different format. But the more challenging part is to deal with the differences in information, right? How can you align like a microscopy picture with a DFT calculation? How do you identify what's similar in them? What is like joint information and what is like completely disjoint information? And usually in material science, it's the material that makes the connection, right? Or one of the aspects that can make the connection. And this is like where the challenge then really begins when it comes to defining metadata, to finding schemas that work for multiple methods, or at least that have parts that work for multiple methods. This is also where ontologies come in order to make sense of all the data, and so on and so forth. Yeah, so in essence, in order to combine data and make it available in a common platform or in a shared platform, we have to get rid of the data format, like we have to get rid of the color, and then we at least have to integrate different symbols, right? And find ways to find like these hierarchies that then allow you to represent information in a common hierarchy, even though that information might be different. And in NOMAD, it works a little bit like this. We have our parsers that go for different file formats and try to convert this into an archive. I wrote this here in blue, like all the blue parts coming directly from the parser. Let's say if a parser looked at the simulation, it produces like this section 1, which then contains the data about the simulation. If it tries to parse like the data that comes from experiments, for example, like a measurement of some sort, it produces a completely different hierarchy of information. But then we have another part, and this is where we try to join the pieces of information. That's the red part here. That's our results section, where we basically try to identify, okay, what is the material that was simulated, or what is the material that was observed with the measurement, and extract this information into a common place. And also have a common place where we try to structure all the method information that went into this. So even though that we are talking about different methods, like a DFT calculation, completely different from like taking a microscopy picture, for example, but there are still similarities when you think in terms of hierarchies, right? You have a DFT calculation on one side, but you might have a molecular dynamics simulation on the other side. They're different methods and they might produce different metadata, but there are also some common metadata. For example, for both of them, you use a computer program to do the simulation, right? So the program name, the program version, maybe the operating system or some numeric parameters might be the same or might share some metadata. And this is what we try to do with these hierarchies, like put the more common information more on top and the more detailed information more on the bottom, and then somehow make this available through a search interface so that you can really select, like either you are on the top level, you're just interested in materials, you want to see everything for a material, or you want to dive deep and go to certain methods and then filter based on certain criteria that these methods offer. Let's say for you are looking for a certain DFT code or for a certain functionality that is used or something like this. Okay, let me skip this very technical stuff. Maybe a few words on our architecture. We try to make the whole NOMAD thing as coherent as possible. So we have like one large source base. We try to use as less tools as are feasible. So everything is based on Python. We use just one framework for doing the API. We have a processing framework. And then we have like lots and lots of these parsers, of course. But everything is connected with one source code project, and then we generate one Docker image from this project and one Python package from this project. And then the Docker image is what we use to operate the system. But everything is like together. It's not like 20 services that are then operated independently. It's basically one image that you have to spin up in your environment, and then you can basically sort of NOMAD. There are a few databases attached and stuff like this. But we try to make it as simple as possible to foster the idea that others might also be able to install this and run this. And we are at a point where we have like a very short tutorial on what's necessary to run NOMAD. And we have like the first 5 institutes that are now running in OASIS that we're able to deal with this. So it's just physicists that are able to run this software and maintain it locally and have these OASIS run. Yeah, that's sort of like the core idea about the architecture that I want to convey here in the little time that I have. And let's go on and talk a little bit more about the OASIS and different use cases that we have for the OASIS. So I talked about the OASIS quite a lot already, right? So I think I understand that this is the idea of having NOMAD at your local institute. But why would you do this? What are like typical use case scenarios for this? So we have the NOMAD software and it can run in different scenarios. The most important scenario for us is of course our central installation, where we basically have a huge amount of public data, then some private data, embargoed data, or data that's not yet published. And we have our central user management and stuff like this one. But then, of course, there are different things that you could also use the software for. For example, you just want to manage your data locally, right? You don't want to publish it yet. You just want to manage it locally. And once you think your data is ready, then you want to publish it and push it to the central system. This is what you might call the academic OASIS. Then we have other scenarios where you want to build a NOMAD mirror, just because, like, I don't know, you are in a far distant country, and the connections isn't always this what you want to have. And if you want to have like larger amounts of data available, maybe you want to build a local mirror of NOMAD. That might be another use case. So basically you take all the public data and mirror it. Then we have the industry OASIS, like let's say industry wants to do like large scale analysis on all the data that we have using artificial intelligence and stuff like this. But of course, industry is industry and they don't really want to see anybody what they are doing. So they don't really want to use the central NOMAD. They rather use a mirror of all the public data, but then also manage their local data, of course, use their own local user management. So really don't have any connection to the internet at all and just run the OASIS in private. And then, of course, we have the FAIR-MAT OASIS. This is like what we want to do in FAIR-MAT, where we have like each institute is run its own NOMAD, and then they work on the data locally, either public or private. It really depends on the use case. But some of the data they want to make public, right? So mostly the metadata for their experiments and stuff like this, they want to make public and transfer to the central NOMAD, while the larger part of the data remains in the repositories. Yeah, so these are the common use cases for the NOMAD OASIS. And now it's basically up to us to make the software as flexible as possible to foster all these use cases. And we already made the first steps, and it's now installable in a pretty easy fashion. And then we also can make a connection to the central NOMAD, like on your OASIS. If you have some data, you can press a button, and it's automatically going through the internet into the central system. It's not right. I have more slides, but for some reason they don't show up. But maybe my time is already up, and maybe it's a good point in time to stop here. Yeah, so I think in summary, I showed you a little bit what NOMAD is, how it works internally a little bit, and I also talked about this FAIR-MAT idea. And how we want to use NOMAD to connect like multiple institutes to each other. And the core ideas are that we really want to have like this domain specificity. We are deliberately chosen this bottom-up approach where we use parsers to dissect different data formats and then try to homogenize it after the fact, because we believe this works much better than to just try to dictate data formats to everybody, which usually doesn't really work. That's one key aspect. And another key aspect is that we really want to build this network, because we believe, okay, data is really big, especially when you look in experiments and certain methods there. You can't have just one server where you try to put all your data. It doesn't really work. You really have to build this network. But of course, data has to be fair. You have to be able to find it everywhere. And this is what we want to achieve with this central portal, or the whole FAIR-MAT idea, where we use one central metadata repository, basically, in order to allow the search and then access the data in different installations. Yeah, okay. Yeah, thank you very much. Let me end with this picture here. Hopefully it will inspire a few questions. Yeah, thank you again for listening.
Okay, thank you. Thanks, Markus. So are there any questions about a NOMAD and a FAIR-MAD?
I have one question here in Louvain.
Yes,
hello.
please.
I have a very general question because, as you mentioned, NOMAD has been around for quite a while, and you listed how many people visit the website and so on. So is there any data on how useful things turn out to be? I mean, are there new breakthroughs, papers? Is there some statistics on the actual effect of NOMAD in this particular case?
I think that this is very difficult to achieve. I know what you mean, and it certainly will be necessary in the future to actually demonstrate that this really works and has an effect. But of course, the questions arise: how do you do this, right? One thing that we try to do, even though they are not yet really public statistics about it, is to track the references of the DOIs that people create with NOMAD, right? So what people can do when they uploaded the data, they can create data sets and have a DOI for this. And in principle, you could do the Google Scholar thing and try to look where these DOIs were actually used, how many publications are there with data in NOMAD. But this does not really tell us really how much this was used. But then you really have to look at the citations to make sense of this. That's one way to go about it, right? To go through publications and try to find something there. Otherwise, we only have like statistics on how many people are using this, right? We can look at our servers and see how many people are requesting something, how many people are downloading something. But then we only make assumptions about what they might do with it, right? And how successful they might be with it. Yeah, but that's the ideas that we have in this regard. At some point, we really want to have these statistics and also make them publish publicly available. Yeah, but that's what I can say to this question, I guess. Maybe you have better ideas on how to do this, how to actually track the usage of a database, and not just how it was used, but also how much was the impact that was generated from this.
I definitely don't have better ideas, but I was, because you say DOE here, so. But sometimes people use, say, 100,000 data points, right, from all over the place in artificial intelligence. And so I don't think that's going to be referenced in any paper. Yeah. So a lot of this will be hidden.
Yeah, but this is another thing that we want to enable, right? We want to also enable people to create data sets for data that they use in an analysis, right? So when we think about data sets, so the data set isn't really the data you uploaded. The data set is really, you can look at the data that's there and you can create a data set from this, right? It's like a tag or a label or like an album or whatever. And then you can make reference to this. So in principle, you could write a paper and reference like a set of data that you use for analysis instead of just referencing your own data.
Okay, thank you.
Yeah. I can read some questions from the chat if you like.
Yeah, and there is also some raised hands, so you can start from the chat maybe.
Maybe we start with the raised hands because I get the feeling they are directed towards the last question.
Then it's Matthias.
Actually, mine is related to the last question because it would be really great in measuring the impact. But of course, a lot of the impact is that people look what is there and then they don't have to redo the calculation again. And of course, I mean, that will never be cited. And you said actually some people may just use the data and do it for use it for artificial intelligence. They should cite it, but very often they will not. So any ideas how to measure impact from the broader audience would be really great. And we like really to do that if you give us really an idea. But it should be, of course, not too restrictive, right? I mean, you still actually like to keep the privacy of people. So any ideas from anyone in this group here would be actually great to learn.
Claudia?
Yeah, I actually wanted to say exactly the same. So if I see how my group, for instance, is using the data, they just avoid doing calculations again, or they use input files and check outputs if they get the same results and so. So I think there's a lot of impact which we cannot measure. So I think it's just along the lines what Matthias just said.
So then I would continue with the chat if it's fine, or is there more?
There's still one question. There's one question here in Louvain from Michael.
Okay.
Thank you very much. I have one question about maybe the inner working in NOMAD. Do you have any projects or developments going on where you try to put links between entries? For instance, if you would say, this entry is a structure that is basically a supercell of this structure with this kind of defect, or this calculation seems to be an interface between this material and that material.
Yeah, so I mean, there are a number of things I could mention in this direction. Like one is the encyclopedia itself, which makes a connection based on the material. And at the moment, this is like very simple, where we basically just create, where we say, okay, if it's the same letters in a similar letters with the same symmetry and stuff like this, and we say, okay, this is like it's the same material and make connections like this. This of course wouldn't catch like stuff like this. Another thing that I could say is that we at least try to make most of the metadata that's relevant for these kind of questions available through the search interface, and you could try to make these connections for yourself if you're really interested. Let's say you have a structure that has a certain defects, and you also know the normal, the idealized whatever structure that would fit the defect. You could basically search for both and try to make the connection. In the encyclopedia, we have a few ways to do automated, no, maybe not, let's not go there. Then the last thing I wanted to say is like workflows is like a big driver for connections that we actually try to formalize. That's a key point currently in our development. We are looking at various workflow engines and try to gather the information that they saw about the workflow in order to make a connection there. So that let's say you do like let's say constants kind of thing where you use like various DFT calculations together to compute elastic constants, for example, that you can really see, okay, these were the calculations that went into this, or like phonons are another thing. Or so we currently have support like for certain specific workflow codes, like PhonoPy, for example. But we really want to broaden this to the more generic approaches where you use like a workflow engine like Fireworks or ASE, ASR, these kind of things, and help users to persist the connections that they have between the data points in NOMAD. And this also for the whole FAIR-MAT thing, very important there. There are other questions in the chat that go in this direction. How do you add, how you allow users to add their own piece of information, right? So our parsers only detect what's in there, what's in the VAST calculation, for example, but they have a really hard time in detecting why you are doing the VAST calculation and how it's connected to other calculations, and really want to enable the user to basically provide these links for us, so to make it easier. But this is also then, like, besides technical challenges, also has like this cultural impact, because when people really have to spend some time and some effort in actually curating the data and going the extra mile to provide more metadata than just what we can discover automatically.
Yeah, I think this is a very important point to try to make these connections. And I think maybe the big success here is that people can just upload data without doing too much work, right? So I think if your amount of data starts growing, and there would be some automated processes to try to automatically find, just based on the structures, these kind of connections, I think that would greatly enhance the usefulness of the results in the database.
I think workflows can be like a short-term kind of thing to attack this, and in the longer term, like artificial intelligence, ontologies, all these kind of more miracle machines might have some potential to help us there to do these automated connections. And of course, these are all technologies that we look into.
So I just wanted to add to the question that a little bit of that is there already. So we are looking, for example, for similarities. So Claudia's group has really a concept that you'd say, actually, I would like to really have materials which have a similar density of states as this one, and then you get really the results. And so in the encyclopedia and in the artificial toolkit, we are exactly really developing these things to find similar properties, which at the end you then really will result in materials which you could actually combine even.
Yeah. That was the point that I wasn't daring to dive into, because it's more complicated if you want to look at it in detail. Yeah, but yes, this is like one example project where we are trying to do. And on a technical level, I mean, there's also like other initiatives that we have where we want to look into these sub-descriptors for structures, and this way it's really more about machine learning and things to make connections. And yeah. I feel like there's in any case, there's like a great potential for future work and research in these areas. And this is also what we want to enable with something like NOMAD, like making the data available would be the first step for people to find new mechanisms and new methods to make these connections.
Maybe you can take the two questions that are in the chat, Markus.
Yeah, Andreas Pönicke is asking if the decentralized approach of NOMAD Oasis, how does it achieve persistence of the data? So I think the idea is that many research institutes have a hard time to deal with this on their own when it really comes to long-term persistence and storing stuff for like forever, basically. And how we want to do this in the centralized architecture, in this federated architecture, sorry. So yeah, the idea is that we think of the available data as pyramid, and in this pyramid you have like more useful data and less useful data. Typically you produce large amounts of data that you typically then just throw away, right? You were just doing experiments that is just garbage data that came out. Then along the research process, you refine your data more and more, and lots of it is like filtering, right? And then the data becomes more and more valuable along the road. Let's say you've done lots of pictures and identified those pictures that actually gave you some clean data, and then from there you start further analysis, and then you provide like a more condensed version of this, and so on and so forth. And at the very top, you have like this nice picture that you put in your paper, right? And this is like how typically it works. And the idea is like when we are limited in what we can actually preserve in a long time, just because the size is super large and whatnot, we want to facilitate these pyramids and say, okay, for the very top, for the published data, for the high quality data, this is where we can offer something. And this is then where you just want to centralize data and put it into a central system that's hosted by research and by HPC centers and data centers that know what they're doing, and then have the long-term persistence there. So there might be 2 or 3 mirrors of the central node that are capable of taking some amount of data from the various institutes, so that we can at least store or at least have long-term persistence for published data or for high-quality data. How much of the pyramid we can store then really depends on how much data is there, how the just network technology, storage technology, and so on develop over the years. I hope that answers the questions at least a little bit. Yeah, the short answer, of course, is we can't really store all data and have like long-term persistence for everything. We're just producing too much. I mean, there are instruments that are producing like terabytes per second, where you basically need special storage structures just to keep the data for a couple of seconds, and then you have to throw them away because there's just too much information coming out of the sensors. So there has to be some clipping at some point, and you have to make decisions on what's valuable and what's not. There's another question from Matthew Evans. Yeah, for computational data, we have well-defined inputs and outputs, but for experimental data, the outputs, question mark, from an instrument where we typically have no knowledge of the system, of the sample, the system, or whatever, at least it's up to the user to manually enter this. Do you think parsers for existing electron notebooks is enough to capture the complexities of experimental inputs? When it comes to constituents, materials, synthesis conditions, processing parameters, and so on and so forth. I think for this question, the workflow part is really valuable. And I think this is what ELNs will hopefully provide us with the connections, not so much the data itself, but the connections between different data points. If you think about that the sample came from somewhere, it was probably synthesized somewhere, and then you do some characteristics on the sample with certain measurements, and then you send the sample around and then use it here and there and so on and so forth. But the idea is like, if all the data is available and we find a good mechanism, for example, to identify samples, you could basically draw a history of the sample, right, and see in what measurements it was used and so on and so forth. Thereby getting idea how the sample might have changed. I mean, that's another aspect where the sample might not, like some of the methods might be to some degree destructive or whatever. Then you get an idea of what the sample was, and you also make connections between all these measurements, and thereby might get an idea of what was actually measured, what was lying under the microscope, and so forth. On the other hand, it will greatly depend on user input, and as you mentioned, that's certainly a weak point, and the divergence from our NOMAD approach, where we do everything with parsers and stuff like this. You have to provide people with like many input opportunities. Electronic lab workbooks are certainly the more common way to do this. And then the question is how to formalize these lab notebooks. Like some lab notebooks are really just notebooks, right? Where you just write down arbitrary text and it doesn't really help you. So one aspect of FAIR is to develop like these laboratory information systems together with lab notebooks, so that you have like a tight integration between the various instruments, and then really have formal kind of metadata entry masks and forms and stuff like this, where you ask for certain information. But still, of course, you never know what the user enters in there, right? And how reliable this is. But again, as with all data in NOMAD, we just have to provide even more metadata to allow you to make assumptions about how reliable some information is. This is also a problem that we currently have with computational data, right? We have all this computational data in there, but we can't really tell people how good the data is. They have to discover this themselves, and we providing the metadata for this, right? We say what the functions are and what the parameters are, and everything is there. And then you have to make a decision on your own how reliable this data might be. And maybe in the future, all kinds of ontologies and artificial intelligence might help you there. And then it's related to the other questions that we already answered a little bit. Yeah, I hope that helps you, Matthew.
Thank you, Markus. Claudia, I saw that you lowered your hand. If it's not important, then maybe you can take a break, because otherwise it's going to be very short. It's okay? Okay. So we can reconvene in 22 minutes then. See you later. Thank you all.
Bye-bye. Thank you.
Yeah.